In 2019, Terence Tao established a breakthrough partial result on the Collatz conjecture. Since then, the mathematical literature has attempted to turn his qualitative result into a fully effective theorem by applying Baker's theorem to control the geometry of his renewal process. This coordinate system represents the discrete JL lattice used in Tao's framework. The process is tracked by identifying sets of lattice points called black triangles. These geometric structures are generated locally whenever a specific phase, the local cosine factor, shrinks below a designated threshold. This 5-node flowchart illustrates the strict logical chain required to render the exceptional set finite. You start with a Diophantine bound, which translates into explicit maximum sizes for these black triangles. Those sizes dictate the minimum gaps between them. The gap control produces an effective Fourier decay rate, which finally bounds the exceptional set. The first computational link in this chain relies on integer variables fixed by an ambient three-adic precision constraint, denoted as n. Everything downstream inherits its functional form from this initial step. A Collatz paper making these claims is worth taking seriously to the extent its geometric bounds are mathematically reproducible. You must be able to take its formulas, compute with them independently, and derive the stated bounds directly from Tao's original definitions. Recent literature contains a critical mathematical misconception at the very first arrow of the logical chain. Researchers have assumed that the diameter of a black triangle, S, scales inversely with the Diophantine approximation quality, given as the absolute value of lambda. Specifically, the literature posits a reciprocal-linear relationship, claiming that the triangle size S is proportional to 1 over the denominator Q times the absolute value of lambda. A rigorous calculation directly from Tao's own formulas proves this assumption false. The true relationship between the geometric size and the approximation quality is logarithmic, not reciprocal-linear. Because the size dictates the gaps, and the gaps dictate the decay rate, applying the wrong functional form here compromises the entire proof. The effective decay rate downstream is built on a faulty geometric foundation. Correcting this functional form transforms the current results. It replaces the sub-exponential bounds found in recent papers with more restrictive polynomial bounds. To find the true relationship, we have to start with the exact parameter for blackness in Tao's framework. A lattice point is declared black when its signed fractional part, defined as theta of j, l, has an absolute value less than or equal to a fixed small threshold epsilon. This equation is Tao's exact formulation for that phase. To understand how this local phase behaves, we evaluate the dominant term inside the fractional part, the pure geometric contribution, given by xi times 3 to the 2j times 2 to the l. We can algebraically unspool this modular condition on the group z mod 3 to the n z. By dividing out 3 to the 2j and rearranging the terms, we convert the modular restraint into a real approximation inequality. This sets an upper bound on the distance to an integer m. Taking the logarithm of that result isolates a two-term linear form, defined here as lambda. This equals L times the natural log of 2 minus k times the natural log of 3, with the height b bounded by the maximum of L and k. The absolute value of the corner phase, theta star, is directly proportional to this linear form lambda. We have successfully bridged the geometric behavior of the lattice to a strict Diophantine approximation.
Recall the literature's unverified claim that triangle size S relates reciprocal-linearly to this approximation quality. This split-screen comparison highlights the contradiction. On the left is the literature's posited scaling. On the right is equation 7.17, pulled directly from the proof of Tao's lemma 7.4. It states the absolute value of the corner phase equals epsilon times e to the negative s delta. Rearranging Tao's literal definition to solve for size reveals that s delta is exactly the natural logarithm of epsilon divided by the absolute value of the corner phase. When we substitute our derived linear form lambda for the corner phase, the resulting size s scales as the natural logarithm of 1 over lambda. These two formulas represent distinct functional classes. The difference shows why heuristic scaling analogies cannot replace strict algebraic derivation from the phase definition. The modern Matveyev and Baker-Wustholz theorems provide a fully effective lower bound for our linear form, establishing a limit on how closely the log base 2 of 3 can be approximated by rationals. This equation shows what happens if you substitute the Baker lower bound into the literature's incorrect reciprocal linear model. The math forces an extra exponentiation, resulting in an exponential bound on the maximum triangle size. Now we substitute the exact same Baker bound into the mathematically correct logarithmic model. The natural logarithm of the true geometric definition cancels the exponentiation inherent in Baker's bound. Using the correct definition restricts the maximum size of any black triangle to a polynomial bound of the height b, granting computable geometric control. Controlling the size of a single triangle is only the first step. To calculate the distance between triangles, the gap variable d, we must also determine how frequently they occur across the unit interval. This frequency is governed by the distribution of the fractional parts of k log base 2 of 3. To bound the deviation of this distribution from a perfectly even spread, we use the Erdős-Turán inequality. This equation displays the extreme discrepancy, dn. The parameter alpha is a fixed positive constant, strictly determined by the data of the linear form, bounded by 1 over kappa. Inserting conservative Matviev constants guarantees that even for n equal to 1 million, the discrepancy error term remains microscopic. It is bounded by a slowly decaying exponential times 10 to the 12th, which is negligible relative to the main density term, 2 epsilon. This discrepancy bound rigorously proves the triangles appear with the expected frequency and controlled gaps. We now have the quantitative density control required to proceed to the Fourier decay rate. Returning to our 5-step flowchart, we update the explicit diameter node with the newly derived mathematically sound polynomial bound. Because the functional form of the diameter and the triangle density are now fixed, the explicit gaps between these triangles can be rederived. These corrected, quantifiable gaps force the two-dimensional renewal process to travel a specific measurable distance through white points every time it exits a black triangle. That forced traversal converts the number of white hits up to time n into an explicit function of n and the Baker constants. This sequence yields a fully effective, computable Fourier decay rate. In analytic number theory, precision is the only path to a valid result. By adhering strictly to stated mathematical definitions, a flawed sequence of bounds is transformed into a rigorous machine-computable limit on the Collatz exceptional set.